Titanium is stronger than steel, lighter than aluminum, and more corrosion-resistant than gold. Yet 99% of people have never seen pure titanium metal in their entire lives. This incredible material powers jet engines that carry millions of passengers safely through the sky, enables spacecraft to survive the vacuum of space, and makes possible medical implants that can last a human lifetime inside the body. But here's what's absolutely mind-blowing. Titanium is the fourth most abundant structural metal in Earth's crust. Yet producing pure titanium metal requires one of the most complex and energy-intensive manufacturing processes ever developed by human engineering. Today we're breaking down the extraordinary journey from raw titanium ore to pristine metal at one of the world's most advanced titanium production facilities, where millions of tons of ore get transformed into the aerospace-grade metal that makes modern aviation possible. Make sure to subscribe as we explore the incredible science and engineering behind creating Earth's most remarkable structural metal. The story begins in some of the most remote mining locations on our planet, where massive open-pit operations extract titanium-bearing minerals from geological formations that took millions of years to create. The primary source isn't pure titanium. It's a black mineral called ilmenite that contains roughly 50% titanium dioxide mixed with iron oxide. These deposits formed when ancient magma flows cooled slowly deep underground, allowing heavy titanium minerals to concentrate into economically viable ore bodies. Modern titanium mining operations look like carefully orchestrated industrial symphonies, with enormous excavation equipment working around the clock to extract ore from deposits that can extend hundreds of feet below the surface. Mining trucks capable of carrying 300 tons per load transport the raw ore to processing facilities, where the real complexity begins. Each truckload represents weeks of careful geological analysis to ensure the ore contains sufficient titanium content to justify the enormous processing costs ahead. The initial beneficiation process separates titanium minerals from worthless rock using a combination of crushing, grinding, and magnetic separation techniques. Massive ball mills, each containing over 100 tons of steel grinding balls, pulverize the ore into particles smaller than sand grains. This grinding process consumes enormous amounts of energy, requiring electric motors that draw enough power to supply a small city. But the particle size must be precisely controlled to enable efficient separation. Magnetic separation systems exploit the different magnetic properties of titanium minerals versus waste rock. Powerful electromagnets create magnetic fields over 10,000 times stronger than Earth's natural magnetism, attracting iron-bearing minerals while allowing non-magnetic titanium compounds to pass through unaffected. The precision of this separation process determines the efficiency of all subsequent processing steps, making it absolutely critical to the entire operation. The concentrated titanium minerals then undergo chemical processing that transforms them into titanium dioxide, a white powder that serves as the starting material for metal production. This isn't simple chemistry. It requires either the sulfate process or the chloride process, both involving temperatures exceeding 1,000 degrees Fahrenheit and chemical reactions that must be controlled with pharmaceutical precision to prevent dangerous side reactions. The sulfate process begins by dissolving ilmenite in concentrated sulfuric acid, creating a reaction so violent it requires massive cooling systems to prevent runaway temperature increases. The resulting solution undergoes multiple purification steps that remove iron, aluminum, and other impurities that would contaminate the final titanium product. Crystallization processes then precipitate pure titanium dioxide from the purified solution, creating the snow-white powder that will eventually become metallic titanium. Storage and handling of these intermediate products requires specialized infrastructure because titanium compounds can be extremely reactive under certain conditions. Climate-controlled warehouses maintain precise temperature and humidity levels to prevent unwanted chemical reactions, while automated material handling systems minimize human exposure to potentially hazardous processing chemicals. Even microscopic contamination at this stage could ruin entire batches of final metal products. Quality control throughout the mineral processing stages involves continuous chemical analysis, using techniques that can detect impurities at concentrations below 10 parts per million. X-ray fluorescence spectroscopy provides real-time monitoring of titanium content, while atomic absorption spectroscopy verifies the absence of trace metals that could compromise the performance of aerospace applications requiring absolute material purity. The purified titanium dioxide now faces the most challenging transformation in all of metallurgy: conversion from oxide to pure metal. This process, called the Kroll Process, requires such extreme conditions and precise control that it remained a closely guarded industrial secret for decades after its development in the 1940s. The complexity is staggering, involving chemical reactions at temperatures exceeding 1,800 degrees Fahrenheit in environments completely free of oxygen and water vapor. Preparing titanium dioxide for the Kroll process requires mixing it with petroleum coke and chlorine gas in massive rotary kilns that operate like controlled chemical volcanoes. This creates titanium tetrachloride, a liquid that boils at 300 degrees Fahrenheit and reacts violently with moisture, making its handling an engineering challenge that requires specialized equipment and extreme safety protocols. The entire facility operates under stringent environmental controls to prevent any accidental release of processing chemicals. The Kroll process represents one of the most extreme manufacturing operations on Earth, requiring conditions so harsh they would destroy conventional industrial equipment in minutes. Massive steel reactors, each weighing over 200 tons and lined with special refractory materials, contain the violent chemical reactions that strip oxygen atoms from titanium compounds. These reactors operate under argon atmospheres so pure that oxygen contamination must be kept below 5 parts per million, because even trace amounts of oxygen would immediately reoxidize the titanium being produced. The magic begins when titanium tetrachloride gets injected into reactors containing molten magnesium heated to exactly 1,900 degrees Fahrenheit. What happens next defies imagination. The magnesium literally steals oxygen atoms from the titanium compound, creating pure metallic titanium and magnesium chloride in a reaction so energetic it could power a small explosion if not carefully controlled. The temperature control during this process requires precision measured in single degrees because variations would create titanium with inconsistent properties. But this isn't molten titanium flowing like liquid steel. The Kroll process creates what's called titanium sponge, a porous metallic structure that looks like a gray coral reef made of pure metal. This sponge forms as individual titanium atoms deposit onto seed crystals, gradually building up a three-dimensional network of interconnected metal fibers. The reaction takes over 72 hours to complete, with computer-controlled systems continuously monitoring temperature, pressure, and chemical composition. Removing the titanium sponge from reactors requires extraordinary care because the material is pyrophoric, meaning it can spontaneously ignite in air if handled improperly. Specialized atmospheric control systems flood the reactor chambers with ultra-pure argon gas, while hydraulic systems carefully extract the sponge without exposing it to oxygen or moisture. Workers wear full environmental suits and operate through sealed glove boxes to prevent any contamination of the pristine metal. The recovered titanium sponge undergoes intensive purification to remove residual magnesium and magnesium chloride that could compromise the final metal quality. Vacuum distillation systems heat the sponge to over 2,000 degrees Fahrenheit under pressures less than 1/1,000,000th of atmospheric pressure, causing impurities to vaporize and separate from the pure titanium. This process requires specialized furnaces with heating elements made from tungsten, the only material that can withstand these extreme conditions without melting. Quality analysis of titanium sponge involves testing that surpasses pharmaceutical standards. Mass spectrometry systems can detect trace impurities at concentrations below 1 part per million, while mechanical testing verifies that the sponge will produce titanium with the strength and ductility required for aerospace applications. Chemical analysis checks for over 30 different elements that could affect final metal properties, because aerospace manufacturers require absolute certainty about material composition. The purified titanium sponge now faces another extreme transformation: conversion from porous sponge to dense metal through a process called vacuum arc remelting. This involves creating an electric arc between titanium electrodes in a vacuum chamber, generating temperatures exceeding 6,000 degrees Fahrenheit. At these temperatures, titanium doesn't just melt, it becomes a plasma where individual atoms exist in an ionized state. Vacuum arc remelting furnaces represent marvels of electrical engineering, consuming enough power to supply 10,000 homes while maintaining vacuum levels so extreme that molecules can travel several feet without colliding with other molecules. Water-cooled copper crucibles contain the molten titanium while electromagnetic fields shape and control the plasma arc. The process creates ingots weighing up to 20 tons, each one representing millions of dollars worth of aerospace-grade titanium. But even this isn't the end of the metallurgical journey. Titanium ingots undergo multiple remelting cycles to achieve the homogeneity required for critical applications. Each remelting cycle further purifies the metal and eliminates segregation that could create weak spots in finished products. Some aerospace applications require titanium that has been remelted up to 3 times, creating material so pure and consistent that individual ingots can cost over $1 million. The solidified titanium ingots emerge from remelting furnaces as massive cylindrical blocks of gleaming metal that represent the culmination of one of industry's most complex manufacturing processes. These ingots have a distinctive metallic luster unlike any other material, with a surface that reflects light in ways that immediately identify them as something extraordinary. But transforming these ingots into useful products requires yet another series of extreme manufacturing processes. Hot working of titanium requires temperatures exceeding 2,000 degrees Fahrenheit and forces measured in thousands of tons, because titanium becomes extremely difficult to deform as it cools. Massive hydraulic presses, some capable of exerting 50,000 tons of force, slowly squeeze and shape the hot ingots into basic forms like slabs, billets, and bars. The deformation must proceed slowly to prevent cracking, because titanium has very limited ductility at room temperature. Forging operations use computer-controlled hammers weighing up to 100 tons to shape titanium into complex geometries required for aerospace components. The metal must be reheated repeatedly during forging, because it work hardens rapidly, becoming brittle if deformed too much at any single temperature. Each heating cycle requires precise atmosphere control to prevent surface oxidation that would contaminate the final products. Rolling mills designed specifically for titanium processing reduce thick slabs into sheets and plates with thickness tolerances measured in thousandths of an inch. These mills operate at slower speeds than steel rolling equipment because titanium generates enormous friction that could cause surface defects if the rolling speed is too high. The rolling process can reduce a 4-inch thick slab to quarter-inch plate through dozens of individual rolling passes. The final processing stages transform rough titanium mill products into precision components that must meet specifications, so demanding they would challenge the accuracy of Swiss watchmaking. Heat treatment processes subject titanium parts to carefully controlled temperature cycles that optimize their microstructure for specific applications. Aerospace components might require solution treatment at 1,800 degrees Fahrenheit, followed by aging at 1,000 degrees for exactly 4 hours, with temperature variations limited to plus or minus 5 degrees throughout the entire process. Machining titanium presents unique challenges that have revolutionized manufacturing technology. Conventional cutting tools would wear out in minutes when machining titanium because the metal's low thermal conductivity causes heat to concentrate at cutting edges, literally melting carbide tools. Specialized titanium machining requires diamond-coated cutting tools, flood cooling with high-pressure coolant systems, and cutting speeds precisely controlled to prevent work hardening that would make further machining impossible. The precision required for aerospace titanium components defies imagination. Turbine blades must maintain airfoil shapes accurate to within 0.005 of an inch across their entire surface, because even microscopic deviations would disrupt airflow and reduce engine efficiency. Surface roughness specifications require finishes smoother than a mirror, achieved through multiple grinding and polishing operations using diamond abrasives finer than face powder. Quality control for finished titanium products involves testing protocols more rigorous than those used for nuclear reactor components. Every single piece undergoes ultrasonic inspection that can detect internal flaws smaller than pinheads, because even microscopic defects could propagate into catastrophic failures under the extreme stresses of jet engine operation. Eddy current testing verifies surface integrity, while radiographic inspection reveals any internal porosity or inclusions. Mechanical testing subjects sample parts to loads far exceeding their intended service conditions. Tensile testing pulls specimens until they break, verifying that the titanium achieves strength levels exceeding 100,000 pounds per square inch. Fatigue testing cycles components through millions of loading cycles that simulate decades of airline service, ensuring that parts will never fail unexpectedly during critical flight operations. Chemical analysis of finished titanium products requires precision that surpasses analytical chemistry used in pharmaceutical research. Glow discharge mass spectrometry can detect impurities at concentrations below 1 part per billion, while X-ray photoelectron spectroscopy analyzes surface composition to depths measured in atomic layers. These analyses ensure that every titanium component meets the exacting purity requirements demanded by aerospace manufacturers. The environmental impact of titanium production has driven continuous innovation in manufacturing efficiency and waste reduction. Energy recovery systems capture waste heat from high-temperature processes, reducing overall energy consumption by over 30% compared to older production methods. Closed-loop water systems recycle cooling water through filtration and treatment processes that prevent any contaminated discharge to the environment. Recycling of titanium scrap has become a critical component of sustainable production because the metal retains its properties indefinitely through multiple recycling cycles. Advanced sorting technologies can separate titanium alloys by composition, ensuring that recycled material meets the same quality standards as virgin metal. This recycling capability reduces the environmental impact of titanium production while making the metal more economically accessible for widespread applications. The economic significance of titanium production extends far beyond the aerospace industry that consumes the majority of production. Medical device manufacturers rely on titanium's biocompatibility for implants that must function flawlessly inside the human body for decades. Chemical processing industries use titanium's corrosion resistance for equipment that handles acids strong enough to dissolve steel. Even consumer products like high-end sporting goods benefit from titanium's unique combination of strength and lightweight. Advanced titanium alloys continue pushing the boundaries of material science through precise control of alloying elements and processing conditions. Titanium aluminides offer strength retention at temperatures where conventional titanium would soften, enabling more efficient jet engines that operate at higher temperatures. Beta titanium alloys provide enhanced formability for complex-shaped components while maintaining the corrosion resistance that makes titanium irreplaceable in marine applications. The production facility operates with computer-integrated manufacturing systems that coordinate every aspect of production from raw material receipt through final product shipment. Real-time monitoring tracks the location and processing status of every piece of titanium throughout the facility, ensuring complete traceability that aerospace manufacturers require for safety-critical components. Statistical process control identifies trends before they affect product quality, maintaining consistency across millions of individual processing operations. Research and development efforts continuously work to reduce the cost and complexity of titanium production while expanding its applications into new markets. Breakthrough technologies like direct reduction processes could eliminate the energy-intensive Kroll process, potentially reducing titanium costs by 50%. Advanced powder metallurgy techniques enable near-net shape manufacturing that minimizes waste while achieving complex geometries impossible through conventional processing. The transformation from raw titanium ore to finished aerospace components represents one of humanity's greatest achievements in extractive metallurgy and precision manufacturing. Every titanium part in a modern jetliner began as black sand in a remote mine, survived temperatures hot enough to melt copper, and emerged as engineered perfection, capable of withstanding forces that would destroy conventional materials. This incredible manufacturing capability enables the aviation industry that connects our world and the space exploration programs that extend human presence beyond Earth. This remarkable facility processes over 2 million tons of titanium ore annually, producing enough finished titanium to manufacture components for thousands of commercial aircraft, while supporting applications ranging from medical implants to chemical processing equipment. The next time you board an airplane, remember that titanium components throughout the aircraft began their journey as ordinary beach sand and underwent one of the most complex manufacturing processes ever developed by human engineering. And there you have it, the absolutely extraordinary process of transforming millions of tons of titanium ore into the aerospace-grade metal that makes modern aviation possible. The precision, complexity, and technological sophistication required to produce titanium showcases the incredible potential of human engineering and materials science. What other industrial processes would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.